Alright, the last part of chapter 8 was just talking about estimating a population mean. You can use the z-distribution to estimate the population mean if you know the population standard deviation. And this right here would be the formula. We also use that z-interval. However, it's just not going to be realistic that you would know the population standard deviation if you're trying to estimate the population mean. Again, that was the formula that we had there. We also had a formula for minimum sample size, so that's the margin of error piece there. You can rearrange that and solve for n if you want. And then basically you're just solving that formula for n. So here's an example about monkeys. They wanted to estimate the mean cholesterol level of a particular variety of monkey. They wanted their estimate to be within 1 milligram per deciliter, so that's the margin of error, at a 95% confidence level. And the previous study involving this suggests the standard deviation is about 5. So if I just go back and look at this formula here, the 95% translates to the 1.96. The standard deviation is the 5 that I'm going to use there. And then n is what I'm looking for, and the margin of error they gave me in that problem to be 1. So they set up this equation here, and then they're just going to solve that for n. So they multiply both sides first by the square root of n. They square both sides. And then the minimum sample size, remember you always round that up, so they rounded up to 97. Like I said, it's not very likely that you're going to know the population standard deviation. It's more likely that you're going to have to use the sample standard deviation. If you have to use the sample standard deviation, then things change a little bit. So if I'm not using sigma, I'm using the sample value, things are different. So this new value doesn't have a normal distribution. It's called the t-distribution. It has a slightly different shape, but it's still symmetric with a single peak at 0. There's just more area in the tails. So here's, you can see, here's your t, so there's just more area out here than there is in the normal. It tells us how far away x bar is from the mean in standard deviation units. And also, there's a different distribution for each sample size specified by the degrees of freedom. When we found the degrees of freedom, it was just n minus 1. So again, here's your standard normal curve. These are two different t-distributions right here. Remember the t-distribution, it's very similar in that they're both all centered at 0. They all have this bell-shaped curve. They all have an area of 1. But then what happens with that t-distribution, it just has more area in the tails. But as that degrees of freedom they get higher, this t-distribution approaches the standard normal. Alright, there was a table, there'll be a table in the AP exam that you can use. I usually taught you to use inverse t, though, instead. So what we would have done here, instead of using, so if I went into 95% confidence interval based on a sample size of 12, we would have done so I would have had you gone to second vars, and I would have had to use inverse t, and if it's 95%, so 95% is in the middle, so there's 0.025 in each tail, comma the degrees of freedom. The degrees of freedom are 11 here. Oops, I lost that. There we go. All right, so then we would have gotten 2.0220, sorry, 2.201, which is what they found here also when they intersect. And remember, we're going to ignore that negative sign because the formula itself already has the plus or minus in it. So when you're doing the confidence interval, if you have to use the sample standard deviation, your formula is x bar plus or minus t star times the sample standard deviation divided by the square root of n. So everything's the same here except you're just getting that critical value from the t distribution and your standard deviation is coming from the sample. We still have the same conditions that we had before, so it has to be random, it has to be normal, or the sample size is large. Again, if you don't know anything about that, you can always check a graph. That 10% condition has to be met unless the observations are independent. This is just another way of looking at all that. So in this example right here, they wanted to estimate the true mean tension of all the video terminals produced at a 90%. So they're going to use one sample t interval. We were told the data come from a random sample of 20 screens. The sample size is small. We must check. So it says here we must check if it's reasonable to believe. So we're going to examine the distribution. So they looked at a graph here. So that's what I was saying. Like sometimes you have to look at a graph. You can either create a histogram, a box plot, or do the normal probability plot on your calculator. Whichever one you choose, just draw a sketch of it and then just state what you see. Remember, you're safe to use the t-distribution as long as there's no strong skew or obvious outliers. Like I said, just always make sure you draw that little graph next to it, though, and then make the statement about it. And you only need to pick one. And then they check the independent check. Alright, once they have the independent check, they have their x bar, there's their standard deviation. They look up their critical value. Again, I would use inverse t. They plug everything into the formula. They come up with their confidence interval. And then they're able to conclude. And the statement is the same way it's been before. So 90% confident in the interval blank to blank captures the true mean tension in the entire batch of video terminals produced that day. Alright, like I said in that last example, sometimes we can, we have some ways of getting around the t-distribution with the t-distribution if it says it doesn't say anything about it being normal. So the t-distribution is called robust because the procedure will remain fairly accurate when a condition for using the procedure is violated. So when we're dealing with the when we're using the t-distribution, and if we have a small sample, as long as the sample being random is going to be more important than the sample being normal, or than the population being normal. So for that normal condition, some things that we can do to get around it. I'm basically kind of here, if you look at these two, there's pretty similar here. If it's less than 15, they really want it to be closer to looking normal, so it's roughly symmetric, single peak, no outliers. If it's at least 15, then they're saying that, well, you have some leeway there. Maybe there could be some outliers or some skew. I kind of lump these two together, though, and just say you're always looking for no strong skew or no outliers. If you have large samples, you can use them for clearly skewed distributions as long as your sample is greater than 30. And that was basically everything we discussed in that chapter.